Good morning. Myself, Prabharan J, working as an assistant professor in EC department at SNS College of Technology. In this lecture video, I am going to talk about the topic name is CMOS inverter DC characteristics from the Unit 1 MOS transistor principle of VLSI design subject. Let I discuss. These are the topics covered by this lecture video: introduction, DC response, logic level and noise margin, activity, transient response, and assessments. Okay, let we see one by one. Yeah. Yeah. In DC characteristics of a CMOS inverter, describe its behavior under steady-state conditions, providing insights into how the inverter process and output digital signals based on input voltage. Here, an introduction to CMOS inverter DC characteristics. CMOS inverter is composed of two complementary MOSFETs. One is NMOS transistor, another one is PMOS transistor. NMOS transistor, another one is PMOS transistor. NMOS transistor connected between the output and ground activated by a high input voltage, and PMOS transistor connected between VDD and the output activated by a low input voltage. And DC response, specifically the voltage transfer characteristics, describe how the output voltage of a logic gate varies with the input voltage when operating under steady state DC conditions. Let's discuss the VTC for a typical CMOS inverter, which is a fundamental example of a gate in digital logic circuits. CMOS inverter voltage transfer characteristics. CMOS inverter structure. CMOS inverter consists of PMOS transistor connected in series between VDD, which is supply voltage, and the output Vout. NMOS transistor connected between the Vout and ground. The gate terminal of both transistors are connected together, and serve as the input Vin to the inverter. V in equal to 0, V out equal to yeah, you can see the here, when V in equal to 0, V out equal to VDD. When V in equal to VDD, V out equal to 0. In between, V out depends on the transistor size and current. By KCL must settle such that IDSN equal to modulus of IDSN. Yeah, next is we will discuss the transistor operation. Already you know the transistor are fundamental components in electronics, crucial for amplification and switching application. Their operation depends on the type of transistor, such as bipolar junction BJT or field effect transistor, and the configuration in which they are used: common emitter, common collector for BJT, or enhancement depletion mode for FFT. Sorry, FET. Here first, we overview of I will give the overview of transistor BJT operation. BJT transistor operation. Bipolar junction transistor consists of three doped semiconductor region, emitter base collector, two types, NPN and PNP. PNP operation modes. You know the operators mode. Active mode in NPN, emitter base junction forward bias, base collector junction reverse bias. In PNP, emitter base junction forward bias, base collector junction reverse bias. Current flows from the emitter to collector. Current gain beta equal to IC divided by IB. Saturation mode emitter base and base collector junction both forward bias. Reduced current gain used for switching application. Cutoff mode both junction reverse bias negligible collector current. Okay, this is the cutoff region, linear region, saturation region, and NMOS operation. In cutoff region, VGSN less than VTN. In linear region, VGSN greater than VTN, whereas drain VDSN less than VGSN minus VTN. In saturated region, VGSN greater than VTN, VDSN greater than VGSN minus VTN. NMOS operation VGSN equal to VN, V in, VDSN equal to V out. You can see the diagram. Similarly, PMOS operation where VGSP equal to V in minus VDD, VDSP equal to V out minus VDD. Here you can see the PMOS diagram. VTP less than 0. This is the current voltage characteristics make PMOS is wider than NMOS such that beta N equal to beta P. This is the current versus V out, comma V in. And load line analysis for given V in, plot IDSN, IDSP versus V out, and V out must be where current are equal. Load line analysis. Load line analysis. This is the DC transfer curve. Revisit transistor operating region. Region A, NMOS is in cutoff region and PMOS is in linear region, where region B, NMOS is in saturation region, PMOS linear. Similarly, C, saturation, and both are in saturation. D, NMOS is linear, PMOS is saturation, and E region linear and cutoff. Next one is noise margin. Noise margin is a crucial concept in digital electronics, especially in the design and analysis of logic circuit. It refers to the measure of a circuit's tolerance to noise or interference in the input signal before the circuit produces an incorrect output. Noise margin is the amount of voltage or current, whether it is voltage or current difference between the signal levels representing logic high 1, which means 1, or logic low, which means 0, that ensure a reliable circuit operation. Yeah, logical high, logic low. Purpose of noise margin is it ensure that variation in input signal level due to noise, voltage fluctuation, or other interference do not cause the circuit to misinterrupt a logic circuit. Noise margin provide a buffer against uncertainties in signal level, enhancing the reliability and robustness of digital circuits. Types of, here you can see types of noise margin: high level noise margin, low level noise margin. This is the logic level. To maximize noise margin, select logic level at unity gain point of DC transfer characteristics. Next is transient response. DC analysis tell us V out if V in is constant. Transient analysis tell us V out of T if V in of T changes. Requires solving differential equations. This is the assessment of this lecture. If you have any doubt, you can ask me through the comment. We will meet in next video. Thank you.